Okay. So like I said, we're talking about internal flow. We've been going through maybe the momentum part of it. We're going to go through the thermal part of it and maybe understand the differences there. So let's see, just to remember where we left off. So last time, this mess of a slide, we were going through, we developed a momentum, conservation of momentum balance here, and wrote out our equation, canceled out a bunch of terms, and then we ended up with this simplified thing here. So let me just rewrite this, and then we'll continue doing some analysis on this equation. So rewriting this, we had the pressure term, so we have minus dP dx equals the shear stress, tau s, times perimeter over AC, plus d dx of this integral 1 over AC, area integral of rho times u squared times dA. So that's our form, and I guess what we're trying to do here is use this to relate, let's say, the pressure drop, which is a function of position. So you have this dP dx, relate that to the shear stress at the surface, and then this last term over here, which is the acceleration. Right? There's this change in momentum associated with getting this core over here. Right? You're coming in at this uniform velocity here, and as this accelerates, even though the average velocity stays the same, the momentum doesn't, because you have this u squared. Right? U squared favors the higher velocity in terms of momentum. So you have an increase in momentum. That increase in momentum has to be counteracted by the pressure, or the pressure loss. Let's maybe conceptually use that equation to look at what we would expect from pressure drop as a function of position. So let's just write a little, sketch out a little plot here on this coordinate. Let's say this is our position x, and then we're plotting the absolute pressure, or I guess the relative pressure. The relative pressure as a function of position. So, okay, so we have this balance up here. We also have this available to us. So this is our local shear stress. Local shear stress at the leading edge at x equals 0 is infinite because the boundary layer thickness is 0. So we know that, and then we know as you get to the fully developed position, the shear stress becomes constant. So knowing that, I guess we could kind of sketch out what we think this will look like. So let's maybe pick a position here for the fully developed flow. So let's say this is x, f, d, h at this position. Let's maybe start with the fully developed region, because that's a little easier to think about. So in the fully developed region, shear stress is constant. That's tau s is constant. So you have this term up here is constant. What happens to this term in the fully developed region? Anybody know? I hear whispers. So okay, we have d dx of something. We're fully developed, right? So fully developed means it's not changing. It goes away. So that last term is going to go away. So what does that tell us? That tells us dP dx is a constant. Right? Okay, so a constant dP dx would look something like, let's say, this. Linear. So we continue to lose pressure in the fully developed region. That's maybe a slightly subtle point. It's fully developed, but we're still losing pressure because there still is a shear stress there. Like it makes sense, right? So we have this constant, but okay, before we get to the fully developed region, what happens there? Okay, we can't throw away that term up there. We have shear stress, that's still there. And in fact, shear stress is going to be even higher because you have boundary layer thickness is growing, right? It's a smaller boundary layer. So you have higher shear stress. So you have these compounding effects where you have acceleration, so that causes pressure. You have shear stress, that causes pressure. So you have, in the developing region, this really significant jump up. So it maybe draw it like this. Right, so in the developing region, you're going to have a really significant jump up where the slope here is much greater than the slope here. All right, and that again is just, it's both of the effects of increased shear stress tau s and acceleration of that fluid, or of the core of the fluid. So if you're modeling a system like this, you probably want to include the entrance effects. I mean, unless it's a really, really long system and you can sort of prove that this contribution is small relative to the overall pressure drop, which will just continue to happen, you're almost always going to want to include the entrance effects because they do significantly affect the total pressure loss in your system. All right? Okay, so that, I guess, is the kind of wrap up of the momentum part from last time. So now let's start talking about the thermal concepts. I guess before we do that, are there any questions on this? Nope. Okay, so let's move on to the thermal part. So internal flow thermal concepts. A lot of this methodology follows the same kind of template as momentum, which is why we do that first. Some things to think about that are maybe slightly different. Okay, we have our external flow over a plate. We have a specified surface temperature is where we're starting with this. So specified surface temperature gives you this temperature profile, and that continues to grow. What happens in the thermal boundary layer? So you have, what are we looking at? So heat transfer coefficient here at the leading edge as this boundary layer grows is going to go from infinite down in external flow. In internal flow, it's going to fully develop and become constant. So same as shear stress there. We have growth of thermal boundary layers. Those thermal boundary layers can meet at some point. I guess the important thing to point out, though, is that the thermal boundary layer and momentum boundary layer can obviously meet at different points. Right, so you could have fully developed momentum boundary layers, but not yet have fully developed thermal and vice versa. Okay. So let's look a little bit more at this. So we have, it's often the case that we want to predict the temperature as a function of position in internal flow. So let's go through some of the subtleties there. First, I'm going to sketch out the velocity or the temperature profiles here so we kind of get a sense of what's going on. So we have internal flow. Let's try this again. And let's pick some positions. So let's say the boundary layers grow like this. They meet at this point. So I want to draw the temperature profile at this point here. Let's draw the temperature profile out here. And then later on, let's draw it up here. So temperature profile, let's say I'm again plotting temperature in this direction. So let's say my surface temperature is here. And so I'm gonna plot surface temperature profile. The temperature here is going to be T-inf, or T-infinity, right? We have T-infinity coming in here. So if I plot this, it would look something like this, right? You have this kind of profile like that. It is still T-inf in the middle here. And then you have, likewise, a profile out to this edge. So yeah, all the gradient happens here, constant. It's not yet affected. It hasn't yet seen anything. And then you kind of move on. So at this point, now we're fully developed thermally. So let's call that, this is position XFDT. At XFDT, I'm holding the surface temperature constant. So my surface temperature is still at that same displacement away from the axis. But the profile is going to look a lot like the velocity profile, where it's this parabolic shape. Everything kind of comes in. Oops, try that again. Kind of comes in and meets at the middle. All right, where this is still TS at this position. This is this is T infinity here. Okay, so that's maybe obvious. What happens when we move further down? All right, we're moving further down we're fully developed. So what's going to happen to the profile as we move down? Maybe that's an ambiguous question, but you'd think it would remain the same because we're fully developed, but it doesn't, right? It doesn't, because you're still transferring heat. there's still a thermal gradient here. There's still a temperature gradient here, so you're still transferring heat. So eventually, as you go to like an infinite position, let's maybe do that first. So if I were to go to an infinite position over here and plotted this out, it would look like, here's my TS, it would just look like this, right? Constant temperature. So in these intermediate positions, you're going to have still TS here, but it's maybe kind of moving up like this. So your core temperature, your minimum temperature here is no longer T infinity. It's something above T infinity. So you can start to see, okay, we've made the assumption here that this is TS, a constrained temperature at the surface. That's a different assumption than if we were to say that there's a fixed heat flux. Because if there's a fixed heat flux, then you're not going to get this. You're never going to get that at the end. There's always going to be a profile to the temperature. So okay, so this is the temperature consideration. If we were to maybe plot this out, where am I going to do this? So let's find a room down here. So what I want to do is plot temperature as a function of position x. And let's say we're going to plot first our surface temperature. So let's say this up here is TS in blue. So TS through our entire position is constant. Let's say we come in down here at T infinity. So if I were to plot, let's say, the average fluid temperature as a function of position, what would it look like? You'd start down here, you're coming in, everything's at T infinity. At an infinite length, everything's at TS. But in the meantime, you have a lot of heat coming in here because the gradient's relatively high. Gradient goes down a little, gradient goes down a little. So your heat transfer rate is kind of going down as you go in that direction. Which means if you were to plot your temperature profile, it would look something like this. Right?
Left-hand side of your I guess you're starting at when fully developed for thermal?
We are starting here at x equals 0 at the leading edge of the plate. So this here is 0. This is x equals 0. So coming into that pipe, everything is at the fluid mean temperature. Everything's at T infinity, right? And then as you go in, you're adding heat to the flow. So you're adding heat to the flow. The amount of heat you're adding is quite high at the beginning because the boundary layer is really thin.
Okay. So that's like a cross-sectional average temperature?
Yes.
Then? Okay.
Yes.
So there's still something that exists at temperature T infinity.
You're saying like right here at the leading edge, there's a surface temperature here that's being forced?
I guess you're not plotting the temperature along the axis.
No, let me give you the definition. So the definition of what I'm giving you here is called the bulk mean temperature, or sometimes called the mixing cup temperature. Not sure why that is, but what it is m dot times c times Tm. So Tm is the mean fluid temperature, which you can get by saying rho c, the area integral of T, right? And T is a function of y, times U is a function of y, dAc, right? Differential of the cross-sectional area. So you're taking the area integral of temperature and of velocity. So it's essentially like a velocity-weighted average temperature. All right, and that's what we're plotting here. So this down here is my T sub m. Okay, so this is the situation if we have a fixed surface temperature. As I said, it's different if we have a fixed heat flux, so we'll maybe talk about that in a minute. Just to kind of tidy this up, I guess, a few maybe definitions or things to think about. So in external flow, we had the situation where if we were to define the heat transfer coefficient using Newton's law of cooling, it would be H is equal to Q dot double prime S over Ts minus T infinity. For internal flow, though, It is slightly different. It's H is equal to Q dot double prime S over Ts minus what's the temperature that we're sort of convecting to. It's no longer T infinity. It's Tm, basically. So we use Ts minus Tm, where Tm has to be computed using the velocity averaged integral.